In this video, I'm going to try and review most of what we covered in velocity analysis using the graphical method. Essentially, we said if there is a link which is pivoted here and is about rotating about this point, then we can determine the velocity of any given point on this link with respect to a fixed position by considering the velocity v magnitude to be equal to the distance to this point r times omega, and the direction would be orthogonal to the position vector of this point. And then we also said that we know the direction based on the sine of omega, so we would have the direction to be this because the omega is in the direction. We arrived at all of this based on the idea that the position vector r of the point is r e to the I theta, and when we take the derivative of r, we get the velocity v, and that is that. So r omega and then tilted by 90 degrees in the positive direction. So if the position vector was this way, the velocity vector would be turned 90 degrees and would form this direction. That's what we saw here. Now, if the same thing, if the same link was mounted on an object which was moving, for example, a slider which had the velocity v in this direction, vs, then we can do the same analysis with respect to the slider. We know that this point, which is at, let's say, an angle theta, has a velocity, angular velocity of omega, and so the velocity v is in this direction. This is with respect to this point, and let's say this point is called as A and this point is called as B. We can say VB with respect to A is given by this V, which can then be written as R omega. The magnitude of VB with respect to A is R omega, whereas the absolute, this is VB with respect to A. The absolute velocity of the point B with respect to a global origin has to be calculated in the following way. VB is VB with respect to the velocity of the point A on the slider, and the velocity of the point A itself should be added to that, which is same as the velocity of the slider Vs. Same as Vs. So these are the two important distinct velocities that we need to know. We need to understand these before we try to solve any of the problems on velocity analysis with mechanisms. So we'll quickly look at some examples. If I take a 4-bar and I consider the input of this 4-bar to be this is at omega 2. I have O2, A, B, and let's say this is C, or let's stick to the O4 convention. This is O2, omega 2. We know this angle is theta 2. This angle is theta 3, and this angle is theta 4. So we can then consider an origin of the coordinate system which has velocities. So these are velocities in the x direction, velocities in the y direction. In this, point O2 and O4 don't have any velocity, so they are both zero vectors of this coordinate system. Note, I've marked the velocity coordinate system separately than the position coordinate system. That helps us distinguish them clearly. From here, I can first mark the velocity of the known point A. We know that the velocity of point A is going to be in this direction. This is VA, that is coming from this length being A, B, and C. We know VA is A times omega 2. That's the magnitude. The direction is based on the angle, based on the position of the point A, which is at theta 2. This angle should be theta 2 plus 90 degrees. Then we can consider point B with respect to A. This is already point A. So from here, we know that the velocity of B with respect to A should be along that line. So we can draw a line parallel to that at this point. We don't know the magnitude of this vector VB with respect to A because um, we are yet to find what is omega 3. We also don't know whether it is this way or this way. Similarly, we don't know whether omega 4 is clockwise or anti-clockwise. We are trying to find these two, but we know based on the fact that O4 doesn't have any velocity and B can be measured with respect to O, we have VB to be perpendicular to BO4. So we can draw a line parallel to that. Now the point B can have only one absolute velocity, and so this intersection can be the only possible solution. We know that we will get VB absolute from O, so this is the direction, and then VB should be equal to B with respect to A plus VA. So we have to follow the loop in that manner. So we go to A, and then in order to get to B, we have to point in this direction. So this is the second vector, which will be VB with respect to A. That completes the velocity triangle for the 4-bar mechanism. We can now obtain the unknown omega 3 and omega 4 from this triangle. Um, so just in order to do that, let's assume that the um, velocities are just represented as VA for the point A here, VB with respect to A when you're measuring B with respect to A, and VB where VB is just being measured with respect to this point. Uh, so that's VB, and these are obtained from the triangle. So you drew this triangle based on the idea that you have a certain magnitude known as R omega, and you have given it an approximate length. Say, for example, you knew VA is equal to A omega 2, and then you're representing A omega 2. A may be something like, say, 4 centimeters, and omega may be something like omega 2 may be 1 radian per second. Then you would have A omega 2 equals 4 centimeters per second. You can choose to represent a scale where 1 centimeter on velocity triangle or the velocity coordinate system is equivalent to 4 centimeter per seconds of actual velocity. Then you can say that uh, maybe we'll mark the velocity. Do we need to? Maybe we don't need to mark them. So we'll just say this is about 1 centimeter. Then you can actually take a scale ruler and just read off this distance. Let's assume that that distance is about 3 centimeters. And then this distance is about 2 centimeters. Then that means the velocity of VB with respect to A, which is the magnitude of which is supposed to be B omega 3, corresponds to 3 centimeters, which would mean 12 centimeters per second. And velocity of B is C omega 4, is 8 centimeters per second in a similar manner. We know B and C, so we can calculate omega 3 and omega 4. So essentially, all I'm saying is once you know the value of VB with respect to A from the velocity triangle, you can divide that by the distance AB and you would get omega 3. And you can take VB, absolute velocity magnitude, divide that by O4B, and you'll get omega 4. By extending this and saying that there is an actual body which is of a certain shape, if we had this body as the coupler and we have a similar setup as to pivoting these points of O2, O3, and we want the velocity of this point P, we can do the whole velocity analysis as done here, and we can say VP. We would at this point we would know what is this delta, say 3, and so we know the R of P is RP with respect to A plus R of A, and we can write R of P is let's just assume a distance P for now, small p. That would be P e to the I theta 3 plus delta 3, and the VP is similarly VP with respect to A plus V of A, and this one would simply be, because P is rotating with angular velocity of omega 3, which has already been obtained from the velocity triangle analysis, and this would be at J, or let me stick to the same I theta 3 plus delta 3. You can do something similar for anything on the input and the output links if they were not simple lines instead of actual rigid bodies. And yeah, that's essentially the 4-bar velocity analysis using the graphical method.